I'll start, Anina?
Yes.
Okay.
Go ahead,
Yeah. So just to recall what we want to do today, where we stopped last time, and because we have to go fast in the end, I will try to summarize a little bit in the last 5 minutes what we were discussing. So just to emphasize, this is our basic setup, that we have some astrophysical objects with momentum, spin, and other multiple movements, which I have just indicated with dots because they will not be important for us, as you will see. They come, they scatter, and they could have of course they have gravitational interaction, but they could have other interactions also, and then they fragment and merge and give us some outgoing objects with mass, spin, etc. And in this process, it will emit lots of radiation, including what we of course finite energy radiation. But our goal is to study, quote unquote, what we are calling low frequency radiation, which is if your detector, the sensitivity of the detector, the detector clicks between some frequency omega, and it's at a direction in the sky which I've indicated as n hat, but the frequency is much smaller than characteristic frequency of the system. So that's the goal. And let me write down the result that we want to prove. So today I will give a sketch of this proof, which is called classical soft theorem, which was a statement that if we now, so just to let me recall some notation, just to emphasize that our metric, we split this metric as where, again, I've just emphasized this is not any, we are not assuming that h is small in any sense, but we are interested in looking at h at very large distance, at infinite distance. And then from h we could define, for example, which is the standard thing you define in linear gravity. These are just definitions, I'm just recalling them. And finally, the object of our interest is, you consider U is just the retarded time. Okay, that's the object of our interest, and this object is what we will call E radiative omega x. Okay, so this I have just slightly paraphrased some of the one formula I wrote last time, but I hope it's clear what we are doing here based on our discussion, that the radiation falls off as this power, and we are only interested in radiation. So that means that whatever metric you compute from Einstein's equation, you take this limit, then everything else will drop out, and only the components we were interested in remain. And so we call it a radiative field. And we did a Fourier transform in the time domain, in the retarded time domain. So that is omega, and this x is the spatial vector, and the dependence on x is of course it's everywhere there. So that's the thing we want to compute. And then let me write down the theorem, which is called classical soft theorem, and I will explain why. I mean, we had a little discussion, but I will just emphasize why this is called a theorem as opposed to just a computation. Is that this E has a certain universality to it if we expand in omega in the following sense, that it can be written, we will prove that it has this form. There will be a normalization that I'll write down in a minute, times K is simply a 4 vector, which I'm just defined it like this. So n hat is the direction in the sky where we are measuring the radiation, and omega is the frequency that. So this is completely fixed by the detector, the detector that we have. Thanks. Yeah, I have pulled out. I have also pulled out. Thank you so much. Yes, exactly. So this is x by mod x. It only depends on the angle. Yeah, that's why only n hat. It's only depending on the n hat. And now you may be surprised that okay, this is not quite compatible with what I have written here, because it looks like this is only. This formula only includes the radiation which is emitted from the particle, but we know that if you take gravitational scattering, gravity also emits, everything which has energy emits gravitational waves. So in particular, even the gravitational radiation could emit gravitational waves. So in principle, this formula have to be, this has to include contribution from gravitational fields, for example, or if you had electromagnetic fields. So I'm just going to write, but of course we will be explicit about it right now, just to not make a mess of the formula, plus contribution of from finite energy as opposed to soft, and you will I will try to explain what this exactly means. Finite energy gravitational radiation. So let me write this formula also, just so that there's a complete formula for us. So this is the radiation emitted by the particles up to order omega to the 0. So as you can see, this is like 1 by omega, but this one is omega to the 0. So this is the first two terms in the radiation emitted from the particle, and there are exactly analogous terms coming from the radiation emitted from the field itself, gravitational field itself. So this contribution I'll write separately here, and this contribution can be written as follows. So where plus, sorry, these are the only long formulas I will write in this, otherwise we will try to make things condensed, because these are final statements. I'm just writing it in complete generality. Now where A and B, I will write the equation for A, B in a minute, but A is the linear momentum flux of the gravitational field. So it is exactly analogous to momentum of a particle. And this B is the angular momentum flux. And you may be puzzled, because you may think that, well, then A also depends on the metric and B also depends on the metric, on the radiation metric. So how can this be an equation? Because both sides depend on E. But as we will discuss in the end, that the dependence of A and B in soft expansion is always of order omega. Of this term and this term is always of order omega. So that means that this really, you should think of it as finite energy gravitational radiation, also sourcing the soft gravitational radiation. So this is not an identity in the sense that think of this two modes. Think of this as a field, which is a field in the soft limit, in the small omega limit, which can be sourced by particles, as well as gravitational fields which are at order higher than the soft frequency. So this will become clear, I hope. If you please ask if something is not clear, at least at the level of the statement. Let me write the expression for A and B. So A mu is the total linear momentum flux, which is so n hat prime is just a direct, so this is the integral over a sphere, sorry I should have said that. So it's just we are just integrating over a sphere. So a mu n hat is the linear momentum of the gravitational field which is emitted in a, emitted in the direction n hat prime. So the formula is no, because this n hat is the fixed thing. The n hat is the direction of the detector. No, n hat is here in the k, because yeah, this is this n hat is the integrated over. So this is n hat prime nu t gravitational mu n hat prime u. So that's the formula. Again, I will have to specify what this quantity is that we will compute towards the end of the lecture. But just think intuitively that this is the total energy, the energy momentum flux of the gravitational radiation, and this is the formula for the linear momentum which is emitted. Total linear momentum, because we are integrating over all times. So we are fixing an angle n hat prime on the sphere. So this is our picture intuitively. And we are integrating over all times, u going from minus infinity to infinity at a fixed angle, and that is this quantity right here. Similarly, B is similar, and B is given by it's the same formula, it's like we just generalize the formula for the So, of course, if you just recall from your, you will be able to relate to this formula in some sense. It's like the angular momentum in a field, but this is really the angular momentum flux that is emitted in a radiation. If you, total angular momentum which is radiated, like that's this thing. So, because you are integrating over all times, so at a fixed angle, what is the total angular momentum which is radiated in a gravitational field? That's this B, and so those are the two objects which enter here. And you can see there's exactly analogous to the structure here. Instead of particle momentum, we have the momentum of the field, and instead of J, we have a B. And just as a nomenclature, because you will have lectures on memory and all, I think, after this. So this thing is called linear memory. And this quantity is called the nonlinear memory. Strictly speaking, this terminology is only in 4 dimensions, but as we will see, hopefully toward the end of this lecture, that even in 4 dimensions, these two terms remain same, whereas these two terms will... because this is proportional to the stress tensor, which is like 2 time derivatives of the okay, so that's the formula that we are selecting. So that's what we want to prove. So I will give a sketch of this proof first in, but only at it's the only at infinity. So you took a large R expansion of the stress tensor and just keep that. That's exactly what. So let me. So I hope that this. So this is the theorem in D greater than 4 dimensions. And there will be a qualitative change in this theorem in D equal to 4 dimensions that we will go to after this, which is actually the heart of our lectures. But to appreciate the nuances, it's important to first look at this proof, which is much simpler than the 4-dimensional proof. So is there any question on the statement at least? we will say something about, you can ask why am I not saying anything about order omega terms. The statement is that, as you can see, that this we have not assumed anything about the theory except that we have a general covariant theory of gravity coupled to whatever matter we have, and so these terms don't care about the theory that we have, and that is why this is called a theorem, because they only, once you specify the initial and final states of your classical scattering, then that completely fixes these two terms in the formula. Whereas once you go beyond order omega, the next term, which is order omega term, that has a term which is independent of a theory, and one term which depends on the higher movements, like the dot 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 that I have written. So order omega term, so the reason I am being pesky about this is because there is a slight difference when you go to order omega and higher order. So let me write it down, although we will not discuss these terms because they are not universal. So there is some order omega term plus order omega square terms. So this order omega term has a structure that we can write which is of this form, but it not only depends on P and J but also on the other multiple moments. Whereas order omega square, there is no such structure at all. So everything has, and that will come out of our theorem. So everything breaks down at this order. No theorem. In the sense that unless I know what is happening in this beyond order omega, unless I know what is happening here, I cannot write down the formula. So I hope this point is very important. So everything after order omega square will be totally out of control for us, and that it will come out of our proof of this theorem. And so for order omega square, there is no universal piece. We have no control over any piece which we will call universal. Okay, so we will see that, yeah. Yeah.
One can also write the first pieces in that way if you consider degravitation to be like the part.
Precisely, exactly. That's a very good point. So you can just think that the summation over A is summation over massive states as well as a flux of massless particles. Then this is the same formula. I just wanted to be explicit because if you in the next lecture series, when they have memory, they have lectures on memory here where they will explicitly see formula like this, so they shouldn't feel we were cheating. Yeah. Okay, so let me now give a sketch of this proof if there are no questions. By the way, is my pace okay? I mean, if it's too fast, please stop me. I think last lecture I went too fast. I wish we had bigger board, bigger blackboard. Yeah. Sliding thingy. Okay. So I will try to keep the red box. Okay, so I will try to keep this box as it is, just to have some reference. Okay, so the proof, sketch of the proof rather. The proof is, so I will try to bring out summarize the main ingredients which are the sort of the main conceptual inputs in the proof. And the first subtlety, where already you see that there is a difference between d greater than 4 and d equal to 4 dimension, is the following, that we assume that. So I will first focus on these terms. No, we will first derive these terms, and then the other terms, because of what it said actually just follows from the extension, so that I will just summarize first. So once we understand a proof for these terms, nothing new conceptually happens in these terms. It's just very technically a bit annoying, but you can find all this in the appendix. By the way, this is this is a review from our paper with Ashok many years, 5 years ago, 2019. So first not assumption, first point is that asymptotically, I should use white, no, sorry. Asymptotically, for every of these particles are, so we will denote the 8th particle with a index like this. And of course, world line of every particle has like they are massive particles, so there is some proper time. Or if they were massless, we would have some affine parameter, but we could always parameterize like this. Okay, so I will explain now this in a minute. So as so this is just a statement that if you go to large distances, if you go to very early or very late times, then the particles become far and far separated, so they become basically like free particles. So now this V is, as I have this I have intentionally not written any argument. It's not a function of sigma because it's just a velocity, initial or final velocity. And the important point is that the deviation from this trajectory is always of this order if you are in d dimensions. So I hope this point is clear because of the fact that in d dimensions, so why is this true? This is true because in d dimensions the potential will fall off as 1 by r to the d minus 2 by 2. So the potential will fall off like this, which means that the force will fall off as the gradient, so it will be r square, so it's 1 by r to the r square in 4D. So this is it's a gradient, right? So it will be 1 higher, right? So d minus 2 by 2 plus 1 4 by d by 2, no, d by 2 and so that implies that if I now get just even you just do Newtonian equations, then you can see that your equation will be now, please ask if this is not clear, I am just giving a dimensional argument as to why this happened, because this would imply that d2x by d sigma square is of this order. And so then you can immediately check that x has to fall off like this for that to happen. And so clearly you see what something goes off in 4 dimensions because this thing get replaced with a log of sigma. So whereas in any dimension higher than 4, particles become asymptotically free. In 4 dimension actually the structure is qualitatively different. They never become free and they always have this logarithmic deceleration coming from long range nature of the force. So that is why the proof, this is the first point where the proof in 4 dimension will become subtle. Yeah.
Under the Coulomb potential, the particles are not exactly free because of the logarithmic.
That's the point exactly. So that as you said, it's also true in Newtonian theory, right? I mean nothing to do with relativity, and that's the point where the proof becomes subtle already because already the first step itself we can't assume particles are free at later early times. Okay, so that's first thing. And now in order to prove this, because the point is that we want to understand what's the radiation which is soft, and by soft we mean that it's the frequency with which we are measuring the radiation is much smaller than the whatever is the characteristic scale of this scattering. Okay, so in particular, just to give an example, if you had a finite impact parameter scattering of 2 particles at some distance b, impact parameter b, then by soft we would mean that the omega frequency of the detector is much less than 1 by mod b. Okay, this is just an aspect to keep in mind. So this is the first point. Second point is we are interested in soft radiation. And so let's see how both of these points materialize for us and give us a nice analytic formulas like this. So first is to just, first to ask, how do I compute this without worrying anything about soft or anything like this? What is the equation that the E have to satisfy? Now, let me write the equation that if we, so please ask if this point is not clear, that if we use harmonic gauge at large distance. So what is extremely important in all this is that we are only interested in radiation. We are not interested in the gravitational field which is here. And so that means that, and large distances, of course, we have assumed that the space-time becomes flat. So that is why we can choose a coordinate system, some inertial coordinate system, and quantitatively write what it means to fix a gauge for solving Einstein's equation only at large distance. And that basically amounts to, as you all know, now if you do this, then the exact Einstein's equation. So let me erase this point. Actually, I should maybe say a little bit more about this. So this doesn't really even require us to be, strictly speaking, this is true even everywhere, because we are simply saying that we are expressing G mu nu as eta mu nu plus H mu nu. So we are just, this G is not perturbative, it's just, we are simply writing it like this, so we have a in some sense a background around which we are doing our computations. But H is not small, so what this means is we have to write the full Einstein's equation in terms of H. But we can always do that by doing the following, that we can write the full if we had, this is the exact Einstein's equation, but we can always write this in the following form. Which is a function of H. So is this point clear what I have done? You simply take this G, you write R in terms of this decomposition. You're not making any approximation. Then you will obviously get one term in this gauge which is like this. Everything else you throw on the right hand side. And whatever else you're throwing on the right hand side, we are calling it local stress tensor of gravity. Now, physically you will be worried that this has no meaning as a stress tensor of gravity at finite x because of general covariance, but that's not important here. This is simply a trick to write exact Einstein's equation in a particular form, right? So there is no approximation that is involved in this equation. And of course, due to Bianchi identity, we see that this total stress tensor is locally conserved just from Bianchi identity. So dou mu, where dou mu again, whenever I write partial, it's respect to this eta. Okay, so I will not explicitly indicate. If you have done this decomposition with respect to some other metric, then everything will be replaced with the covariant derivative of that other background metric. So with respect to eta, we will have this T total mu x equal to 0 just from Bianchi identity. So far everything is exact. We haven't make any approximation. And this is not new, of course, and I think extensive discussion of this in the Weinberg's book, Gravitation and Cosmology, how to write Einstein's equation like in this form, exact Einstein's equation. Okay, so once we have this, then we can now try to express H mu nu in terms of this using retarded Green's function, and we get a following formula. I will not bore you with all the details, but write the formula which is most important for us. By the way, is this okay, or is there any? I mean, actually relativists don't like this because it kind of breaks general covariance, but it's, as a tool it is okay. I think there is no problem with this formulation. But then one can check that, because remember what we are interested in is n hat, which was, I will not again write all the details, but if you remember, it was of the form right, H mu nu. So once you are given this equation, first thing you do is simply write H mu nu x by as so far again everything exact. We haven't make any approximation where the integral is over entire. Oops, sorry. This should be. I apologize. This is E. Not H. Sorry. Remember, E was H minus 1/2. Yeah, and that's if you remember your linear gravity equations also, it's the E that satisfies this equation in the harmonic gauge. So it's just that. And so now the point is that, but this is at any x. So at any x, this is just true, where this is the total stress tensor. So this is not an equation, this is simply an identity. Because both sides depend on E. Right, this the gravity T also depends on E. So this is not some deep thing. We have just written the Einstein's equation in terms of some identity. So it's not, we haven't solved anything. But of course, G retarded is just the usual scalar retarded propagator, which is which we can write in position space. The nature of this in odd and even dimension is drastically different. But in momentum space, they have the same form, and so it's always convenient to start here to do computation. And it's retarded, so I epsilon is sitting in the appropriate place like that. So this is the in any dimension, this is the retarded Green's function. But now we want to do this, like we want to do this stuff. And if you do it, we basically want to take a large x limit. And when you take large x limit here, you have to do some kind of a saddle point expansion. All the details you can find in our paper. So once you do that, you get a following nice equation, relatively simpler equation, which relatively simple identity, I should say. We still don't have any equation. So this component, modulo also the e to the I omega x phase, etc. has it just, if you do the large x expansion, it simplifies like this, where k we have already introduced before. Okay, so now this is a identity for the radiation field, which aims to solve radiation field in terms of the particles and gravitational field everywhere in space-time. Right? So this is just once again, it doesn't have this had a full information of Einstein's equation. This has only a radiative information of the Einstein's equation. But it's a nice integral way to write it, which helps us prove this theorem. So if there's any question about this, please ask at this point. Okay, maybe it's actually this one is very. Am I giving too much detail, Aninda? Should I? It's fine. Okay, so now we will try to use the two observations we had about evaluating this for low frequency. And so the way we approach this is the following. So we one, fix coordinate system. Again, when I say fix, it is not just to do a computation. In the end, our results won't depend on any coordinate system. X prime such that eta is minus dt prime square plus dx prime square. And such that, so that the origin means if you had a black hole collision where the actual collision happens, the center of scattering is at the spatial vector equal to 0. Okay. So this is just some structure we are fixing. Of course, in the end, final result will not depend on all these things at all because of translation invariance. So that's first step. And now the second thing is that divide our process. So let me redraw it. So again, just to emphasize that as a first step, we will only look at radiation emitted from particles. And so as a first step, what we do is, once I have this coordinate system where the center of scattering is at x prime equal to 0 location, we divide this into like just a fiducial box of spatial size L. So we divide our system into two parts, where the boundary of this is at mod x prime equal to L in eta in x prime coordinate system. Again, this L is completely fake. It is just to, it helps us doing calculations, as you will prove the theorem, as you will see. So what we want to do is to say that, well, I'm going to compute first radiation from this, so I'll call this out region, I call this the in region. And so what we want to do is to first compute the radiation coming out of particles from the out region, and separately then from the in region, and then look at the sum of the radiation. Okay, that's the logic. So the fact that particles, if you choose L large enough, then the particles which are outside the L region are at late affine parameter sigma, which means that the trajectories are linear trajectories plus corrections. So the radiation computed from the out region can be obtained by the trajectories that we have, which is free trajectory plus corrections. Okay, of course the radiation from the in region is a messy thing because it depends on all the brute force details of the scattering, but this is where the soft expansion will come into play, that we will see that it will not depend on the details of the scattering, but only depend on the fact that the total stress tensor is conserved, as you will see. So the logic is the following: we first compute things from here, and then we see how computation of the in region for the expansion up to this order in omega will be independent of the actual details of the scattering. Okay, so that's the logic. So first we do out computation and then do in computation, and then we add.
And a picture of time is going upwards.
Yeah, time. So yeah.
Then you should be calling the bottom region the in region and the
No. The in and out is the spatial. Sorry. These are incoming particles. Oh, these are the outgoing particles. This is the this is less than L region, greater than L region. Yeah. So if you choose large L, the space is mostly empty, right? Because the particles are, if they are far away from the center of scattering, they travel and they become far apart, right? Their only interaction is gravitational. So that's why the metric here is really eta plus corrections. But here metric is crazy. We don't know what the metric is in this region. Okay, so let's first compute the out region contribution, because in the out region, this T now is the T of free particles plus correction, right? That's what we, so that's why out region computation is kind of simple. Okay, I will, sorry, I will try to skip some details because otherwise we'll be lagging behind. Everything is there in our paper. So from the out region, let me write the formula first, and then I will give at least some concept, some intuitive argument as to how we get. So E mu nu greater than L region, radiative, of course. So I will write down the result, and then I will explain why it happens. But it is really something very simple, because you just have to substitute the stress tensor for a free particle and just compute this, at large distance. But let me write, and then if you are not happy, we can. Sorry, I'm raising and lowering kind of freely, but because it's respect to eta, so don't mind. Where just to remind you what CA was, the asymptotically the trajectory we parameterized as that's the. Okay, so let me try to explain why this is true. So this plus order omega, sorry, plus order omega. So then, this is the out region. So you take L is as large as you want, and then you just compute. So what I mean by that is that there will be corrections here which go as 1 by L, which I am suppressing, because in the end we'll take L to infinity. We'll remove the box. Box is some fake thing for us. So once you fix the center of scattering, then you say that okay, I'm going to take L to be very far away from the center of scattering. And so then out region is something where particles are far separated, and the only interaction is the massless interaction. So for example, if you have the particles are not charged, then the only interaction in the out region is the gravitational interaction, nothing else. So with that, the statement is that the radiative field at order up to order omega to 0 has this form. And now let me explain why it comes like that quickly. I mean, it's really now like it's just a very simple computation, because we know that. So this is something we did last time, that T mu nu for a particle at a point x is we wrote it as if you remember. Okay, I should put 8th particle maybe. Okay, that's plus higher, plus other terms, plus dot terms, the terms which go as partial square. So now you notice immediately that you take this formula and you immediately notice that the first derivative will bring down 1 power of k. Okay, so if you have 2 derivatives, it will bring down higher powers of k. So if the first term goes as if the first term goes as 1 by omega, which is, if this term, if you could argue that this term, which is no derivative hitting here, goes as 1 by omega, then this term will go as order omega to the 0. And then all the next term will go as order omega and higher. So if you are interested only in first 2 terms, we will not worry about this thing. That just follows from just meditating over this equation. And what is simple? The simple is that outside the box we can think of them as free particles, which means that PA sigma is, so if you are looking at it, if you are looking at the contribution from outside the L region, then PA sigma becomes the asymptotic momentum, momentum of the particle, and RA sigma becomes CA minus VA sigma A. Okay, so you take this, you substitute, and then you do some massaging. It's just a few lines of massaging, and you see that you get this result from the. So nothing else is used except the fact that to leading order the stress tensor is that of a free particle, and we are interested in omega to the 0 contribution. Only these 2 facts. So in this computation there is absolutely no other subtlety. Okay, that's the first statement. Okay, so now we look at the in region, which looks like almost ridiculous, right? Because how we know? But yeah. So let's just try to do that. No, say. I'm hiding a lot of technical, I mean, not important, less important technical details. For example, just for convenience, it's important to, for each particle, you can normalize your sigma such that they are always hitting the L box at sigma A equal to 0. Yeah. Okay, so your particles start at sigma A equal to some, minus infinity, and we can always find for every particle, we can, because affine parameter has affine transformation, so they always hit this box at sigma equal to 0. But these are some, just for simplifying computation, they don't really change the structure of the, is that what you were? Yeah, yeah, okay. So now look at the in region. And of course in region we cannot actually compute because we don't know what is happening inside the in region. So that's another important thing, because if you assume anything about in region, then we will not have a theorem. So we are agnostic here. But let's try to anyway see how much progress we can make. So E mu nu rad omega n hat from the in region is integral over the less than L region right. That's what it is. And this, okay, we cannot do this, but what we can do is the following. We can look at so we can look at, instead of looking at this trying to compute the metric, we can compute its first derivative. That's okay. Now why is this useful? This is useful because this is locally conserved by Bianchi identity, which means this thing simply becomes right. So this is where we use the fact that at least as far as computing this partial information of the radiative metric is concerned, it is enough to know the stress tensor at the boundary of our box and use the local stress tensor conservation law, right? So this it's a full stress tensor, but exactly. And but now the point is that we want to evaluate it at the edge of this box, where of course it is conserved, so it matches with the stress tensor locally of the outgoing particles. So here of course it has the gravitational contribution, which for a moment I am ignoring. I am just going to look at the particle contribution. But this already simplifies the thing. But of course we have not got the metric. We have got only this partial information. So now you substitute at x equal to L the stress tensor, because at large L is again like free trajectory plus correction. Yeah, so that you substitute, and if you do that, then you find that you will get some. So this quantity, let's call it f nu. Of course, we are not interested in f nu. We are interested in E mu nu. Exactly. So I'm not, absolutely. So the way we computed E mu nu out, that's the same way we can compute this information of E mu nu at this boundary by taking free particle. So I'm not boring you with all the detail. We just substitute same stress tensor and compute it. But we don't get the full E, of course. We only get this first derivative of E. So that I'm calling f right now. So so f is some function of, so f turns out to be some function of the momenta sigma and n hat up to order omega square.
There's a black hole, the horizon does not favor.
No, because L is very large, right? So everything black hole, multiple black holes, they are all part of this, the place where we don't know the physics.
Yeah, but then don't you have another boundary?
But that will not matter, right? Because that is all part of this. All the horizon structure, everything is part of this. But if I was computing this quantity, I would need to know it, but not for the first derivative. Right? So again, that was the point, right? That far away from the center of black hole looks like a point particle with multiple moments. So again, same. So horizon structure dissipates as far as this computation is concerned. this particular computation is concerned. And why is it at order omega? Because notice we are computing something which is already linear in omega, because it's like k mu times this. So if you just compute it, you will see that whatever you find is stuff which is sort of only depends on p, sigma and the direction, and terms which we don't know what they are. Now here's the point, that this implies that, so we have f nu, but now here's a claim that given this, I can rewrite a unique E mu nu. So I will explain in a minute why this is true. Sorry, less than L, which is the following. Oh, this everything is inside the sum. So this is my claim. So now I'll argue why this claim is true. That even if you only have the information about f nu from the in region, we can write the solution for the E is unique up to order omega. Okay, and that solution can be read off completely from this point. Okay, so that I'll explain in a minute why it's true. It's a very direct argument. But once that is there, then we have a contribution from the in region up to order omega to the 0. Okay, so is that point clear? So I have now explained why this is true, that there is a unique solution. But if you with that we have both the contributions under control from the part.
The sigma and the c factor the same as the sigma and the c factor.
They are exactly the same. Yeah. So let me now explain. Then we just add this, and then we get our answer, at least from the particles. What radiation we get from them. No. I have not, because I should have done that here also. I just did it differently. So here now, if I expand this, because I am only interested in order omega to 0. So the one will give us a leading term, which is this one. The second term, which is k dot ca, will combine with this to give one omega to the 0 term, and the one here will give us another omega to the 0 term from here. That's it. So nothing, everything else is higher order omega. Yeah. So now let me give the argument as to why this is true, and then we are kind of more or less done for this proof. So I have then I will tell you what point I have hidden after giving this argument. I mean, there's just one point that I have in this summary of the proof. I have not been able to show you where it came, but so why is this true? This is true because we are computing E mu nu from the in region. So the first point is that this is analytic in omega. Why? Because of the fact that we are computing radiation from a compact source. So if you are computing the radiation of the compact source, then nothing. You cannot have a singularity at low omega, right? Because the source don't have any contribution at low omega. Is that point clear? So so what I am saying is that E mu nu rad less than L omega x hat will always go as will be analytic at it's analytic at omega equal to 0. Sorry. Right, because of the fact that omega equal to 0 corresponds to mod x equal to infinity, but the in region has no contribution at mod x equal to infinity. So now let's assume that the solution that we find is not unique. So suppose we say there are two solutions. So we want a solution which is such that limit omega going to 0, E mu rad less than L omega x hat should be 0, because at 0 frequency there can be no contribution from a compact source in a radiation. And secondly, K mu. So if I had two solutions, if I have two solutions, the assertion is that given f, I have a unique E. So let's assume to the contrary that even if I have two E's. So let's call the two E's E and E prime. But then we know this is true. Right? Because both of them are giving the same f. So of course the difference is 0. So we want E which is 0 at omega equal to 0, E prime which is 0 at omega equal to 0, and this statement is true. Now from here you can immediately check that maybe this is like a homework, that so that means if I call this thing delta E mu, then it has to be of the form times some function of n hat. And then of course that's at order omega square. Right? So that is telling us that as far as we are interested in up to these first two terms, in fact it would be true. Notice that this means that even if I went up to order omega, this ambiguity will not hit me. But this ambiguity will really start hitting me if I go to order omega square. And so that means after omega square I completely lose control in this proof. I hope this point is clear, right? We have no unique solution of this. Our proof will not work because it cannot give us any unique solution from the in region as soon as I go beyond order omega square. So the gray area is order omega, which I haven't discussed, but clearly this is telling us that up to order omega to the 0 we have a unique solution. Right? So now all we have to do is add this, of course. And so you see that, as Aninda mentioned, that this has a C hat, they are C hat, and actually they are with the opposite sign, and so they cancel. These two cancel. And now if I add the rest and I do some minor algebra, then, and that minor algebra only requires us to assume one thing, which I'm going to write down. So not assume, use, sorry, I shouldn't say assume. So using so if you have to use this, which is just the angular momentum conservation. Using this we find that E mu rad omega n hat has the following form. So again you may wonder, this is not true because my fields are also carrying angular momentum, but right now I have simply suppressed that contribution. So consistently suppressed it, otherwise we have to include it here also. Or as Sid said, that just think in your mind that the fields are also massless particles, because we have never assumed these P's are massive. So then it works also in that sense. As a heuristically, of course we can do it more rigorously by including fields, as I will explain in a minute maybe. So then this with this, use this, add these two, and you find that the full result for the soft radiative field is where J is simply total angular momentum for the eighth particle at asymptotically. So it's Ca mu P nu minus Ca nu P mu plus sigma mu nu. And remember, K and n hat are directly related because K is simply omega 1 n hat. Okay, so this plus order omega terms. So that's the sketch of the proof of why for any scattering the first two terms are universal in the. The point is that they are both, no, that's an excellent question. The point is that this is really the contribution from the boundary region. So and this is a unit vector. So they come with the opposite because of that. So that's the first point. And now, okay, we have to, if we want to include fields, then we have to start including the stress tensor of the field carefully, and that can be worked out explicitly. You can look at our appendix also, and then it's really exactly the same proof, no other nuance, except it's harder because there is field configuration you have to include, but you have to use the local conservation and conservation of angular momentum, and then the result is what we wrote earlier up to this order with A and B replacing P and J in the No, exactly. Yes, a very good point. So you don't, but because we are interested in radiative field, we are looking at stress tensor at large R, and so then only terms which are quadratic come in, because if you have like a h cube term, it will always go as order 1 by R to the some sufficiently high power so that it doesn't contribute to the radiative E. So we have to do a careful counting. There are some subtleties on odd even, but it can be done, yeah. So you are what you got. Yeah. We use the large X, exactly.
So it is already, I don't know, I saw the saddle point first time in Jeremy's Ranchigo's paper.
Yes. That's what this is. Yes, exactly.
What I mean is that once you do that saddle point approximation,
yes.
it already brings out the power of R.
It already, exactly.
That kills the power of R.
Yes.
Let me put it very positively.
Yeah.
It only keeps the radiative part.
Exactly. Yeah. No, I think Justin was asking about the test tensor itself, which is feeding into E.
That's true. But what I mean is, in the end, you only want the radiative power
of the metric. Yeah.
So whatever stress tensor you have, once you do the saddle point, for the E.
Yeah. No, but I think just to clarify, the point is that in the E itself, even in the radiative field, even in the radiative field, we have a full integral over the source, right? After doing saddle, this is our equation. So I think Justin's question was here. But when you do the soft expansion, you see that every power of, so I should have said it carefully, I'm sorry about this. So you are right that these of course are terms which are order h square and order h cube. But you can estimate that all the terms of order h cube do not contribute up to order omega to the 0. So that's the, because of the fact that you see that what is happening here, that only the free data is contributing, right? The asymptotic momentum and angular momentum is contributing in the end. So that means we expect only the asymptotic momentum and angular momentum to contribute. And then as Sachin said, that one is always only, like asymptotic is only order quadratic in H. So it's tied together like this, that the soft expansion and the radiative field both tell us that only h square term up to h square term contribute to the. Okay, so this gives us the, I don't know Anita, how much can I take? 5 more minutes? The soft, these two terms are not sensitive, but if you go beyond this, of course, then we will have I mean, we can stop here, but if you give me 5 minutes, I can tell you the 4-dimensional subtlety, just at least introduce it.
So somehow one might say that even though you don't do a small h expansion,
yeah,
it's like a derivative and
it's a derivative expansion.
Derivative expansion and sort of an amplitude expansion both happen because of the soft limit, right?
Yeah, exactly. Yeah, I agree completely.
So soft limit gives you both.
Yeah, exactly. Yeah, I mean, as you would, as all of you would have noticed, this one is like a trivial thing. I mean, probably this one is slightly more non-trivial in the sense that to show that this term is also universal, maybe it's not completely obvious. Okay. So now I will just give you in 2 minutes, I will tell you the main subtlety in 4D, which is the heart of our discussion, which we start tomorrow. So the first crazy thing that,
Can I just ask
yeah. No. Thank you. Yes, because we use the following. We said box eta of E mu nu is T mu nu matter plus the rest, T mu nu grav. So if you have any high derivative theory, throw everything else here. Yeah, exactly. So we don't know anything about this in general. That is related to Justin's question also, because we have h cube. So you take any theory of gravity, the quadratic term in T are universal. So as long as our result don't depend on the h cube or higher order terms, it kind of implicitly tells you that the results we have are universal, theory independent. I will just as a small, okay, just 1 minute. I will tell you, because although we didn't discuss it, because there is no proof of it, but because of something we will discuss towards the end of the lecture, that in d greater than 4 dimensions, string theory gives us quantum factorizations for the S matrix, and inspired by that, one can make an educated guess of what this term is. So I just write down, if you are interested in staring over it, which should have this form in d greater than 4 dimensions. But this is a if you want, this is a educated guess in classical theory, just from the structure of factorization in quantum theory. So the order omega term one anticipates, which will have the following form. Again, I'm only focusing right now on the particles. Where this B depends on the higher multiple moments of the object, of the H particle. So this is a guess. We don't have a proof of it, but when we discuss the quantum factorization theorem, you will see why this guess is kind of an educated guess. And what is interesting is that these B's have been computed by Justin Vines and others for Kerr black hole, and they are 0. So because of some Neuer theorem, so that means that at least for in d greater than 4 dimensions, for Kerr, if you have only Kerr and Schwarzschild black hole scattering, then this is the term that you would find. What is important is that even here you see this term, even though it depends on the higher multiple moments, it doesn't depend on the details of the scattering, which is tied to the fact that the non-uniqueness of the solution in the in region came only at order omega square and not order omega. So in that sense, that we can parameterize the radiation up to order omega if we have the control on the multiple moments. But beyond this order, we have no control on the solution at all. Yeah, so this one can call this quasi-universal, because even though they are in terms of asymptotic data, but it's not just the data that we, if you give me a neutron star or a Kerr black hole, these things won't, with the same spin and momentum, this will not be sensitive, but this will be sensitive to that difference. Okay.
Is the vanishing of this related to the vanishing of love?
That's a very good point. It's related to the fact that spin and momentum are the only independent charges for a Kerr black hole. But I don't know if that's directly related to vanishing of love number. I'm not sure if vanishing of love number is tied to Neuer theorem directly. No, I don't know if people have proved it. I don't think so.
But vanishing of love number would show up as.
Sorry, vanishing of love number is only in 4 dimension though, by the way.
It is in 4.
No, this is higher D.
This is in 5.
Yeah. Okay, so maybe I just stop here. I'll just take 2 more minutes, Aninda, if it's fine. Just to give a sort of a overview of what we will do tomorrow, which is the following. So we can make a completely dumb guess as to how to generalize this to 4D. So this is all in D greater than 4. What will happen in 4D? The first thing that will happen is, as we discussed before, that x mu of sigma would no longer have a form, but it would have some as infinity, and this implies that if I look at this term, there is no difference, because this is the asymptotic velocity or asymptotic momentum. But if I look at this term, this has the angular momentum, so J, which is CA wedge, XA wedge PA plus sigma. Now you see clearly it will pick up a term. So in higher dimension it would only have term C wedge P, and then this would be 0, and then terms which will decay with sigma. But now we have a new term which is, so we will have a term which is, maybe I shouldn't call everything C, sorry, D. CA wedge PA, which is a finite angular momentum at late time, but then a divergent contribution. Plus terms which decay. Something I don't remember, sigma I think. So now you notice that, so that means that if I just dumbly take this and substitute it here, I get a term which is diverging at late time in terms of sigma. But now you can say, wait, what is sigma? There is no sigma, I have only there is no time left once I did an integration. So there is only omega. So what's the dumbest guess I could make if I try to substitute this there? And we know that late sigma is low frequency. So the 0th order guess, I mean this is just an argument as to what will happen, is that we could replace this with omega inverse. And it turns out that this dumb guess actually works very precisely when you prove it, that the contribution to this term in 4 dimensions has a log omega contribution, and that log omega contribution is precisely generated by this term here that we will see, which is related to the Coulombic tail. And what is absolutely remarkable is that this log omega term also will be universal, and this is what is called tail to the memory, so that we will discuss more. So maybe now I can. Thanks. It was slow today, slow now.